Okay, as we get into 2.1, we're going to deal with some AP calculus topics here. Topic 1.2, defining limits and using limit notation. In terms of understanding, reasoning with definitions, theorems, and properties can be used to justify claims about limits. In terms of our objective, represent limits analytically using correct notation. Remember, you can always hit pause, look at those essential knowledge statements to get even a more deeper understanding of what's going on. Okay, 1.3 we're going to look at today also, which is estimating limit values from graphs. In terms of understanding, reasoning with definitions, theorems, properties can be used to justify claims about limits. Our objective, estimate limits of functions. Once again, hit pause, take a look at that knowledge. Okay, in 1.4, estimating limit values from tables. We don't necessarily look at tables, but we'll be putting stuff into our calculators. Understanding. Reasoning with definitions, theorems, and properties can be used to justify claims about limits. If you notice, these kind of all gone together. So it's not that we're doing a lot today, we're just doing a lot of we're introducing the topic of a limit and what a limit is about. In this particular topic, our main objective is to estimate limits of functions. Okay, so here we go. Average velocity. If you remember from our previous example here with Wile E. Coyote, our average velocity is simply our change in our position or distance over your change in time. In simply stating in terms of Algebra 1 and things we've been doing our whole math careers, that is the slope between 2 points. Specifically, it's the slope between 2 points of a position function. Okay, instantaneous velocity requires the use of limits. So what we really need to do now, so we can get into what the major concept of what calculus is about, is go ahead and examine limits. Now, limits are what separate calculus from pre-calculus. And when dealing with calculus, you guys, there's two main topics, what we call derivatives and what we call integrals. Both of those dive hard into what an actual limit is about. Okay? One is going forwards, one of them is going backwards. Now we're going to start this whole idea of a limit and look at this graph right here. Hopefully we have an idea of that, but that's a rational function. Okay, it's a rational function which if you put into your calculator would actually look like a line. And the reason why it's going to look at a line is if you factor a little bit and use some of your Algebra 2 skills, you're going to see why. Now, if you look at this, x is not able to equal 2. Why? Because 2 would give us a 0 in the denominator. So our domain here would be negative infinity to 2 union 2 to infinity. Now, if I look at the graph over here, even in my calculator, it looks at x equals 2. It actually looks like I have a value right there. But if you remember from your pre-calc days, that is actually a hole. Why? Because if I plug in a 2, I don't just get 0 in the bottom, I get a 0 also on the top, which we call a removable discontinuity. Now what we're going to do is we're going to look at this table here, and we're going to dive into this a little bit more, and we're going to bring up that idea of a limit, that same idea that we brought up when we looked at what was happening with Wile E. Coyote at a instant value when t equals 3. But now what we're going to do is what's happening to this graph at exactly x equals 2. Okay, so what I did to save us some time here is I went bang. Okay, I filled in all this stuff for you guys. All right, so if we go ahead and look here and we plug all of these x values into our calculator, whether we are approaching 2 from the left-hand side or we are approaching 2 from the right-hand side, you're going to see it darn well looks like it approaches a specific value. Okay, so what exactly is a limit? Okay, the limit of a function is an output, a y value, right? 4 would be an output or a y value. It's a single real value. So we don't say a limit ever goes to infinity or a negative infinity. It has to be a single real value. It's a y value that may or may not be reached, and we don't care. Okay, we don't care if it gets to 4. We just care that it's approaching 4. An limit is an output the function gets really close to as the input gets really close to a number. So as these guys get closer and closer to 2, as these x values get closer and closer to 2, it goes to that specific value of 4. Okay, here's our notation. A limit as x approaches c of f of x equals L. Okay, and L being the limit value. All right, now let's go ahead and let's keep on going here. And let's go back to our notes page. Okay, if we look at this thing now, okay, let's scroll up here a little bit. So the important question which we just got done with is, what is the limit as x approaches 2 of f of x for that graph we were just looking at? Remember, if we plug in a 2 into that value, I get a 0 over 0. But the limit approaches from the left and to the right, they both go to 4. So that is what we call our limit value. Now, to really understand limits, it's always very, very helpful to look at piecewise functions. So let's go ahead and look at this piecewise function. Let's go ahead and graph it first, and then we're going to go ahead and look at what's happening to that in terms of a limit. Okay, but when x is not 2, our value of y is always going to be 1. So what would that look like? Well, when x is not 2, so that's kind of like how I would graph that. Okay, when x is not 2, our y value is always going to be 1. But when x is 2, our y value is going to be 0. So that's how I would graph that piecewise function. Now, if you look, whether you're approaching 2 from the left-hand side or from the right-hand side, it looks like it goes to a specific y value of 1. So let's go. The limit as x approaches 2 of our piecewise function g of x is equal to 1, which is interesting. So even though the value is not 1, the limit is 1. And that's what happens with the idea and the concept of limits. Okay, let's dive a little bit deeper into limits now. If you notice, we've been looking at these as we go from the left to the right, but sometimes they don't always equal the same value. So we have what we call one-sided limits. Okay? In dealing with one-sided limits, there's some notation that we have to be very familiar with, okay? And it's all right here in our notes, beautifully stated. Okay, this is how we say the limit as x approaches c from the right-hand side. And as we approach c from the right-hand side, our limit value is L. Doesn't matter that that's the function value, it's where do we approach as we come from the right-hand side. Now this one right here would be what is our limit of f of x as x approaches c from the left? And this would be from the left-hand side. And that value doesn't even matter that there's a removable discontinuity, or not a removable, that would actually be a jump discontinuity right there, but that value is actually k. So if you notice, the left and the right-hand side here do not equal the same value, which is going to end up being a very important concept when we deal with continuity and limits in AP Calculus. So what the heck is a limit again? Definition of a limit as x equals c. The limit of a function as x approaches any number c exists if and only if the limit as x approaches c from the right-hand side is equal to the limit as x approaches c from the left-hand side. Then, if they're the same exact answer, L and L, we can say the limit as x approaches c is L. A fancy way, right? This bad boy means IFF in math terms, if and only if. Okay, so it has to be the same from the left and from the right-hand side for us to say the limit exists at that value. Got to be the same. Let's take a look at it with example 3. Now, what I want you to do is hit pause, and I want to see your skills here. And can you graph example 3 in the next 30 seconds? Take a quick pause and get it graphed. Okay, so graphing this, what I hope you did is I hope you looked at what was in question here. And what's in question here is what happens at 2. So let's graph 5 minus 2x. Okay, and I want to start this at x equals 2. So if I plug a 2 into that bad boy, I would get 5 minus 4 is equal to 1. So I'm going to start that at 2 comma 1. And it doesn't have an equal sign, so at 2 comma 1, I'm going to put an open circle. Now I'm only going to use to the right side of that. Okay, so let's go on to the right of that. And if you look, there has a slope of negative 2 over 1. So that's down 2 over 1, down 2 over 1, down 2 over 1. Connect the dots, and there is your graph for the top half of that. Now, same thing, x equals 2. What would that guy look like? Well, let's do some math. You get 6 minus 1, which is equal to 5. So at 2 comma 5, 2 comma 5, and guess what? I can color that bad boy in. Why? Because I got an equal sign right there. Now that has a slope of 3. That means up 3 over 1. Up, but I can't go that way. We're on the left-hand side. So instead of going up 3 over 1, I can go down 3 into the left one. Down 3 to the to, whoops, to the left one. Down 3 to the left one. Draw a straight line through that. Now that looks like some funky graph, but you know what? Piecewise functions really give us an idea about what limits are about. So let's go ahead and answer these next couple of questions. What is the limit as x approaches 2 from the right of f of x? Well, if it's from the right, I'm going to use that top bad boy. Okay, and if I look here, from the right would be from this side right here. And where do I go? Where does that go? It looks like it gets closer and closer to a y value of 1. Okay, now let's go ahead and inspect this graph, or the limit as x approaches 2 from the left of f of x. Now, from the left means I'm going to use the bottom guy. Okay, from the left means coming from this guy. Ooh, wow, that dude gets pretty high. Looks like we get to a value of 5. So D says, what can you say about the limit as x approaches 2? If you notice, there's no left or right-hand side on that bad boy. But what we say is the limit as x approaches 2 of f of x does not exist because the limit, and this is enough validation to say it, the limit as x approaches, not c, I'm sorry, 2 from the left-hand side does not equal the limit as x approaches 2 from the right-hand side. And remember, if they don't equal the same value, then we say that the limit at that point does not exist. What's up, class? So when do limits not exist? That's what's going to become important here. If there does not exist a number L satisfying the condition in the definition, then we say the limit as x approaches c of f of x does not exist. Now, typically, when does this happen? There's really three ways that we get a DNE when looking at limits. 1, f of x approaches a different number from the right-hand side as it does from the left-hand side. 2, f of x increases or decreases without bound as x approaches c. Now that usually has the idea of a asymptote involved with it. And then 3, one we don't deal with much, but when we do it, you'll understand why the limit doesn't exist, but it's when a function oscillates between two fixed values as x approaches c. All right, so let's go ahead and take a look at some examples of when limits don't exist. Okay, we just went from one from the left and the right-hand side it didn't. So we got one kind of taken care of. But what would something like 2 be? Well, this is a very famous function that we all kind of always forget how this guy looks. What the heck does that graph look like? Well, believe it or not, if you put in the same negative, if you put in a negative value for x, for anything, you're going to get -1 as your answer. So graphically, what it's going to look like, anything negative is going to look like that. Now, why am I putting an open circle there? Well, that's at x equals 0. And at x equals 0, I'm going to get 0 over 0. Okay? Now, if I put any positive x value in there, we're always going to get an x value, a y value of 1. Okay? And that graph's going to look like that. Boom. What the heck's going on right there? Well, you can look at that, and the limit from the left-hand side is 1. The limit from the right-hand side is 1. That is what we call a jump, is -1 and 1. That is what we call a jump discontinuity. Okay, right? Because there's an error that happens there. And the limit as x approaches 0 from the left of the absolute value of x over x does not equal the limit as x approaches 0 from the right. So what do we say? That limit does not exist. Remember, it's got to go to the same value from the left and from the right-hand side. And that's an example of one. I think I maybe said 2 earlier. I got a little bit excited of some asymptotes. We're going to head and go and do that one right now. Hopefully, at first look with this one, you notice that, hey, something bad is going on here at x equals 1, right? If I put a 1 in there for x, I get 1 over 0, and that's bad. That's not 0 over 0, that's 1 over 0, which means there would be an asymptote at x equals 1, right? There'd be an asymptote right there at x equals 1. Okay, if we want to know what happens here graphically, excuse me, let's see what's happening as we get closer to this idea of a limit, right? What's happening as we approach from the left? What happens when we approach from the right? And to do that, let's go ahead and use a table of values here, okay? And I punched all these in my calculator already for you guys, but you're going to notice that these bad boys get big. 10,000, Okay, I think you put a 0.999 in there, you get 100K. All right, that's pretty darn big. Okay, if we come from the right-hand side, a little bit of symmetry going on here. Symmetry in the math classroom, always super cool, right? Always 100K there. Whoops, 100K. Man, it looks like it does go to the same value. But whenever a graph, from the left it goes to infinity, from the right it goes to infinity. Remember, definition of limits got to go to a specific value. Okay, this does not. So we say that it is DNE. Why? Because it grows without bound. That's an example of our number 2. Okay, it's got to go to a specific y value. This guy grows without bound. You can go right back up here into your notes, right? And if you go back in here and look at your notes, that's our example 2. Increases or decreases without bound as x approaches c. All right, if you're like me, you're dying to see what the heck is this oscillation bad boy talking about. Well, try putting that guy into your calculator. Okay, and I'm gonna plug in some values, okay, as we supposedly get closer and closer to 0. But when I plug in these values, it goes from 1 to -1 to 1 to -1 to 1 to -1 to 1. Okay, and the interesting thing is this guy alternates between 1 and -1. Well, that's an idea of oscillation. Okay, whether we're coming from the left or the right, it just keeps on jumping between 1 and -1. So it does, once again, does not go to a specific value. We're not going to handle that guy much in AP Calculus, but we just wanted to give you the 3 ways in AP Calc how we sometimes deal with when a limit does not exist. All right, class, I hope you're enjoying this so far. It's kind of the part 1 of the first lesson of the year in AP Calculus. Please come to class with your questions. Remember, the coolest thing about flipping this classroom is in class we get to just work on problems. So instead of struggling with your homework at home, we get to struggle on it together in class. I'm always here in the mornings, so make sure you come in with any questions, concerns, or hey, I would love suggestions of how I need to make these videos better so that you guys have a better understanding. Aloha.